Okay, welcome back. I hope everyone is here. So we'll continue with the keynote talk by Justine Boulent, I hope I pronounced it correctly, on whale detection from the viewpoint of satellites. So Justine, do you want to go ahead, share your screen?
Yeah, sure.
Okay, perfect.
Do you see my screen? Yeah. Okay.
Yes, perfect. Thanks.
Thanks for the invitation. I'm really happy to be here to talk about active learning to scale aerial whale monitoring. First, a few words about the company I'm working for, Whaleseeker. We're a Montreal-based company created in 2018. We are B Corp certified, which means we meet high social and environmental standards. And our focus is to leverage AI to improve whale monitoring by delivering better, simpler, and faster whale detection data. Here's the whole team behind the work I'm going to present you. I will start my presentation with some introductory words on aerial whale monitoring. Then I will present the analysis solution we developed at Whaleseeker. And after that, I present an application case using this solution. And I finish my talk with some perspectives about whale monitoring. Whales are very important animal species for ecosystem functioning, as they provide key ecosystem services. In our fight against climate change and biodiversity loss, it's therefore crucial to protect them. And to protect them, we need to know and monitor them better. For that, we need high quality data, both in terms of regularity of acquisition and reliability and transparency of the analysis. Also, we need user-friendly data, which can be interpreted and used by decision makers not necessarily trained in biology. Part of the available data comes from aerial surveys. Typically, an aerial survey consists of several flights over a given area. And on the plane, we can find several biologists who will count the cetaceans observed in real time. The plane is also typically equipped with a camera whose images will be analyzed afterwards for areas where many whales were observed. Often these images are still analyzed by hand, which is a time-consuming and expensive process. Analyzing the survey images will typically require several months for a photo analyst. Manual analysis also leads to intra and inter-observer variability, thus challenging multi-temporal analysis. The current quality of data analysis is not appropriate to meet the challenges of whale conservation, and it's also a bottleneck constraining the acquisition of new data. To improve and accelerate the analysis of this data, we can rely on AI, which has led to great improvements in the automatic counting of animals in recent years. However, automatic aerial surveys analysis is not a completely solved problem, as it's not yet been really adopted for our task. Indeed, there are several challenges to the development of an AI tool. One of them is the variability of the conditions of acquisition. Depending on the flight parameters, the images captured will vary greatly. For example, here you have 3 photos of narwhals taken at different altitudes. And with such differences, it's complicated to have just one model that generalizes well on all this kind of data. Another challenge is the heterogeneity of the marine environment. When someone has never worked on this type of environment, like me before joining Whaleseeker, they can have the false idea that it's a very homogeneous environment. But there is, on the contrary, a lot of diversity depending on the geographical areas, the season, the weather. And last but not least, whales are also quite a challenge to work on because they are scarce targets whose depth varies, which makes them more or less visible depending on their behavior. And also some species live in dense herds, and in this case, individualization is quite difficult. Because all of this, it's a very complicated task to gather a dataset rich enough to automatically analyze all this diversity. The option of developing a single model with an excellent generalization capability is therefore not really adapted to our problem. To be able to automatically analyze new datasets, we chose the active learning approach. The main idea behind active learning is that not all images are equal, and therefore a model can perform very well by being trained only on the most important example of the dataset. The training process works by iteration. Based on the automatic selection algorithm, images will be selected for annotation. I have the video working. And yeah, and this image will then be used to train a model. This process is repeated until the predictions are good enough. This approach leads to flexibility and robustness with only few annotated examples. So let me now talk about the analysis pipeline we have created at Whaleseeker. It's our in-house tool called Mobius. The pipeline consists of three main steps. First, an automatic preliminary analysis. Second, the active learning loop. And finally, a manual review of the prediction by an expert. The purpose of the preliminary analysis is to avoid a cold start to the active learning loop. When we have a new dataset, we don't know much about it, so we'll run some preliminary analysis to find out a bit more before the proper analysis. The first step is the land cover mapping in order to exclude the land areas from the analysis and also to calculate the percentage of water cover on the whole dataset. For this, we use a semantic segmentation model that we train on thousands of annotations. The second step is the environmental diversity mapping. This step ensures that the environmental diversity is well represented in the different training, validation, and test subsets. It also avoids redundancy of the images selected for annotation. To do this, we use a dimension reduction tool, UMAP, to obtain a representation like this one. On this graph, each point represents an image. And roughly speaking, the more two images are similar, the closer they are in the representation. This is what you can see here, where this area, for example, contains tides with images with clear blue water, and on this yellow cluster we have more turbid waters. The last step of the preliminary analysis is an initial segmentation of the whales. Since it's performed with a source model not suited to the target dataset, the results will be very imperfect. For example, here we can see a missed whale. Nevertheless, it allows to find potential whales targets and also potential false prediction. So these imperfect predictions are very useful to start the learning process and to ensure that we have whales as examples in the validation and in the test subsets. So at the end of the preliminary analysis, we have for each image a lens segmentation, an imperfect whale segmentation, and also a location in the UMAP representation. Let's move on to the second major block of our pipeline, the active learning loop. The goal of this step is to fine-tune the source model so that it can correctly analyze the target dataset. Based on the outputs of the preliminary analysis, we will start by selecting images for the validation and test subsets. Using UMAP and imperfect whale segmentation, we will ensure to have a selection representative of the environmental diversity and also to have example of whales. We then enter the active learning loop, which starts by querying images to annotate to train the model. The query algorithm is based on 3 criteria. The first one is the random selection within the different UMAP clusters. The second is a least confidence criterion, which will select the images that contain targets with uncertainty scores close to the decision frontiers. And finally, we have a most confidence criteria, which will select the images that contains targets with a high score. And having those 3 criteria allows to get a diversified selection for training. These images will then be annotated by a marine mammal expert. And with this annotation, the source model is fine-tuned. We can then analyze the test subset with the new model and evaluate its performance. As long as the results are not good enough, we start again with the loop. And once the results are good enough, we terminate the active learning loop and run the prediction on the whole dataset. So we reach the last step of our pipeline. Each prediction is manually checked by an expert to ensure the quality of the final analysis. The expert will open only the images with prediction, and it will verify each of those predictions. So now you know more about the solutions that allow us to scale aerial image analysis. When we think about the use of AI, we often visualize a 100% automatic approach. In our case, we preferred to rely on human expertise for some key steps. In fact, we even see our tool more as an annotation support for human experts. Now I'm going to present an example of a case study. It's a project that we have presented in an article that will be published in the next few weeks. In this project, we worked with a dataset acquired by Fisheries and Oceans Canada in 2017 to monitor the Cumberland Sound beluga whale population. The acronym for Fisheries and Oceans Canada is DFO, and I will use DFO in the rest of my presentation. This dataset of about 5,000 images was entirely analyzed manually by a photo analyst employed by DFO, which took between 8 to 12 months. Since she worked on other projects during a contract, we do not have a more accurate estimate for the work she did on this project only. In this dataset, she detected 4,572 belugas. The objective of the experiment is to compare these results obtained by hand with those of an analysis based on the Mobius active learning pipeline, and to see if similar results can be obtained in less time. First, let's look at what I mean by similar results. In our domain, the ground truth consists of annotations made by a photo analyst. This ground truth, therefore, contains a certain degree of interpretation, which leads to inter-observer variability. Waves and birds are sometimes source of disagreement that we have observed, like in this image, we have falsely whale annotated because of a wave, and here bird annotated as a whale. But the variability is mostly observed in difficult cases, such as when objects are not on the surface, like this one, where we have 3 annotations by different observers. The first one annotated nothing, the second one annotated 1 whale, and the third one annotated 2 whales. The last difficult case is the groups of whales. We can see here that everybody, the 3 observers found this group of whales, but the counts are not matching. So what ground truth should we compare our prediction to? Having a 100% agreement is not an achievable target, since even 2 human experts will not get 100% agreement when annotating the same dataset. Instead of aiming for 100% agreement with a particular expert, we use the minimum inter-observer agreement as a target. The inter-observer agreement is comparable to the intersection over union. So we're comparing the union between the detection of observer A and B over the union of their detection. To calculate this metric for this particular experiment on the DFO dataset, we had 3 different observers to annotate the test subset of 50 images, 2 being from Whaleseeker, observer 1 and observer 2, and observer 3 is the photo analyst who annotated the entire dataset for DFO. We then compared their annotations, and their level of agreement ranged from 88% to 93%. We retained the 88% as the minimum percentage to get between the human observers and the model to stop the active learning loop. Since I have already detailed the method earlier, I will show you directly the results of the training loop. The results displayed in this graph were obtained on the test set, so 50 images. We can see the evolution of the agreement here between the model and the 3 human observers at each iteration. So the 3 observers, the 1 and 2 are from Whaleseeker, and the third one from DFO. And at each iteration, we annotated 50 additional images for the training. So let's look at the numbers. The source model got a little more than 50% of agreement with all human observers. After 1 iteration of the active learning loop, we reached a little over 85%. And at the second iteration, we exceeded our targets of minimum inter-observer agreement, with results going a bit over 90%. We therefore stopped our active learning loop after only 100 annotated images. With this model, we then analyzed the whole data set, and 1 observer from Whaleseeker verified manually all the predictions. Here you have the results on the whole data set. On the left, the number of predictions using our Mobius pipeline, and on the right, the number of detection from DFO's photo analyst. The gap between the 2 analyses is a little more than 270 belugas in absolute numbers. And for the mutual agreement, we reach 84% of mutual agreement. Since we did not have an independent third-party observer to decide where the errors were in both analyses, we only performed a visual observation. The biggest sources of disagreements were the same ones we identified on the test set: depth and dense earths. For more than half of the disagreements, our marine mammal expert felt that the lack of visibility made it impossible to confirm or deny with certainty the presence of belugas. Now we can compare the time spent by the observers to analyze the whole dataset. With the help of the Mobius pipeline, it took only 53 hours to analyze the whole dataset of more than 5,000 images, while it took the DFO photo analysis between 1,000 and 300 hours to a bit beyond 2,000 hours to analyze everything by hand. So with AI assistance, we have a huge time saving for the biologists. This freed up time could be used for other tasks like more advanced analysis based on these detections. Also, it could enable the participation of several biologists to analyze the datasets together, leading to an analysis with less inter-observer variability and thus even more standardized. In conclusion, active learning is truly a robust and flexible solution that enables the integration of AI into our analysis pipelines. And thanks to this, we are able to analyze datasets faster in a more standardized way and in a more advanced way also. With analysis time no longer being such a limiting resource, we can make the most of each dataset to extract all available information. Another advantage with an analysis system like this one, we can consider switching to completely photographic acquisition and thus limit the number of biologists on board during the survey. Using AI to monitor whales opens possibilities far beyond occasional aerial surveys. Thanks to these technologies, we have the possibility to really improve the monitoring of cetaceans by doing regular overflights, for example. But we also have the possibility to limit the impact of human activities on whales. For example, we are exploring through a pilot project the front monitoring of boats in real time to avoid collisions. As in many fields, AI brings really exciting perspectives, and I find it even more exciting when it leads to the development of tools to protect biodiversity and to concretely fight against climate change. Thanks a lot for your attention. Be happy to take the questions.
Thanks, Justine, for a very interesting active learning approach. Are there any questions? Otherwise, I'll start with a question. So the last few slides, you said something about the hours, how long it takes for the active learning pipeline as opposed to the fully manual pipeline. Maybe I didn't really catch that, but was that for the segmentation of all the whales, or was it for segmentation and bounding box? Because you have two types of like annotations, right? Like the segmentations and the bounding box. What was the number referring to?
On our side, we are doing the segmentation, and the biologist will verify all the prediction and individualize the whales if needed. And if I displayed bounding box, it's because the annotation format from DFO was different from ours. It was just a point annotation. So we had to transform it to little bounding box to be able to do the comparison with our segmentation.
All right. So I wonder generally what you want to do. Do you really want to have the segmentation marks? So I wonder, is it necessary to have the segmentation marks as opposed to, like I wonder what tasks you want to tackle. I mean, for purely counting, it would not be necessary to do segmentations, right?
No, right. But the segmentation has the benefit to allow other tasks, like if we want to extract a biological characteristic for each individual, it will be possible with the segmentation mask. And also, the issue with the bounding box is it's not working well also with dense earths. So even if we're choosing to switch to bounding box, our biologists will still have to go check and modify those boxes.
All right, yeah, that makes sense. And one last question maybe from my side. So you use satellite data, and I guess you cannot use any temporal information, right, over a time horizon. You just take static images, right? Is that correct?
No, for this one, it was aerial monitoring with a plane.
Mm-hmm.
Not a satellite one.
Okay.
But yeah, we can have different scenarios. Sometimes it's very punctual surveys because we know that a given species is gathering in a given area, so it's the right time to do the flights. Yeah.
Okay. All right. Perfect. Thank you. All right. If there are no questions, then thanks again, Justine, for a very nice talk. And we'll go to the last point of today's session. Oh, there's actually one more question, Justine, if you can spare 1 minute.
Sure.
So the question from Xiaomin Ling, have you thought of using synthetic data? I believe it sure work well in these cases. Synthetic data would come with masks.
Yes, we started some experimentation at Whaleseeker, but I don't have results to talk about. We didn't do a proper comparison. But yes, great comment.
All right. I definitely see potential in collaboration since Xiaomin Ling is very motivated to do synthetic data. So let's see what comes out of that. All right, thanks. Okay, then we'll go to the panel discussion, and I will hand over to Fabio to do this. And yeah.